Okay, I would like to welcome you to the medal lecture, the von Humboldt medal lecture. As you may be aware, EGU has quite a substantial honors program with medals and awards, and they're division level medals. Each division has a medal to give to outstanding people, and they are union level medals. And one of the union level medals is the von Humboldt medal. And the von Humboldt medal recognizes outstanding people who have been active all over the world to do research at the highest level, and also reach out to different countries in the world, do research in different countries of the world in the spirit of von Humboldt. And I'm particularly pleased to introduce to you this year's recipient of the von Humboldt medal, which is Professor Hubert Savenije from the Technical University of Delft. Hubert, welcome. Oh, yeah.
You have to look at them.
Okay.
Fine. Thank you.
Okay. Just a few sentences about Hubert. He's a professor of hydrology at the TU Delft and did an amazing spectrum of different things. Those that are societally relevant, for which he is getting the award, and also more theoretical thing about the hydrological cycle, global scale hydrology, down to hill slope hydrology. But today it's about water and society, and I can just say the stage will be yours in a second. Before that, I would like to read the citation to you, but it's a little complicated because it's like 4 lines. The 2015 Alexander von Humboldt medal is awarded to Hubert Savenije for outstanding research and for providing superb graduate student training opportunities in developing regions for the benefit of people and society in the field of hydrology, water resources, and estuary water science. So that's the citation. And the medal ceremony will actually be tomorrow, Wednesday in the afternoon. So if you have time, please come, and then you can see the actual ceremony of the medals. So Hubert, now the stage is yours.
Thank you very much, Günther. And I noticed there is even a balcony, so if people want to sit on the balcony, there's a space there. Okay, thank you very much, Günther. I'm really honored with this beautiful prize. The nice thing with von Humboldt is that you don't have to explain to people who von Humboldt was, because he is an extremely famous scientist, at least in Germany, but I would say all over the world. And I'm going to try to dedicate my talk also to subjects that very well fit into von Humboldt's work. But before I do that, I would like to thank a few people, and I put on my glasses because I don't want to forget anybody. But first of all, my great friend Nick van der Giezen, who was so kind to nominate me for this very, very beautiful reward, and the people who supported him. That is Jungwo Liu from Beijing Forestry University, a former student of mine, Nguyen Am Duc from the Vietnamese Mekong Commission, who was so kind to also support my nomination, Stefan Uhlenbroek from the UNESCO IHE, and then Alvaro Carmo Vaz, old friend of mine, professor at the Eduardo Mondlane University in Maputo. And I think thanks to these very nice letters that they wrote, and I forget Dominique Maswi-Mavi from the University of Western Cape in South Africa. So thanks to these strong support letters, I'm very happy that I received this beautiful medal. But let me turn back to von Humboldt. Von Humboldt was a great scientist who lived around 1800. And he fits perfectly in the tradition that we know, maybe of Cook's travels with Banks, who looked into New Zealand, Australia, described the ecology, the geography, measured almost everything that they could. That was in the 18th century. And then, of course, Darwin, who in the 19th century did a lot of investigations all over the world and developed his great theories on evolution. And von Humboldt fits in that. He's in the middle. He's around 1800, and he was somebody who, when he went on his travels, took with him all the most modern equipment that was available at the time and measured virtually everything. And on the basis of that, he developed his ideas and his great theories that later in his life he documented in his standard works. Let me see how I move forward. Is it by clicking? No. Just click what? The slide. Sorry, escape. Can somebody do escape for me? Yeah, I mean, I have nothing to except the mouse. How do I go forward? With the mouse? Like this. All right, good. So, I think many people will know this book by Daniel Kehlmann. It is a novel, and he has the novel about both Gauss and von Humboldt, but it's a very good read. It's based on fact, but it's clearly also a novel. And he describes how von Humboldt went over the world and measured all these things. And the title I've taken is How Observations Lead to Theory. There are also great scientists who said the opposite. And even Einstein said, if observations don't match your theory, then measure again. Yeah? But a less famous scientist who was one of my students, Hugo Hellebrand, I don't know if he's in the room, he said, don't let data spoil your perfect model. Yeah? If necessary, bulldoze the world so that it fits your model. Yeah? So, but I think my idea is that observations come before theory. But let me first say a little bit about von Humboldt's travels. He, in fact, visited large parts of South and Central America. How did he do it? He went to Spain, he traveled to Spain, he visited the Prime Minister of Spain at the time, who was supposed to be the lover of the Queen at that time. And this was the most powerful man in the Spanish kingdom. But he suffered from, let's say, an ailment that comes with age, and he couldn't satisfy the wishes of the Queen every time. And what did von Humboldt say? He said, I'm going to the Amazon, and there are Indians there who have a remedy that can help you. And you have to give me free access, laissez-passer, money and letters that give me access to everything, and I will come back with what you need. Of course, it was a lie, but it was a lie in the interest of science. And this is completely acceptable. So what you see here is that he visited parts of present-day Colombia, and he went to the border with present-day Brazil to investigate a very strange phenomenon, which I, as a hydrologist, find strange. Because he said there is supposed to be a natural canal that links the Orinoco to the Amazon. Now, hydrologists, but also every person who has went to school knows that river basins are separated by a water divide. And a water divide is defined by the fact that water isn't passing the divide, you know? So this is strange. Is there somewhere in South America a natural channel that links two major river basins? And von Humboldt actually went there, and it's described in the book, and it was a terrible voyage through the jungle where they suffered a lot from malaria and everything, but they found this canal. He also went up the volcano here, very high up. This is something that he is famous for because he noticed that as you go up and the pressure drops, the temperature drops, and you move from a hot climate to a cold climate, and that is very similar to moving north towards the poles. This is one of his famous theories. But let me go back to this famous canal. As a hydrologist, I must say I'm surprised by that. Is there something here that links the two river basins? And it's called the Casiquiare Canal. I will come back to it at the end of my talk and give you the opinion of a hydrologist. Was von Humboldt right or wrong? But before that, I will tell you some of my own history. where I started by measuring and later developing theories and modeling. And I will go through 4 subjects. And most of these, if not all, started in Africa. I will start with the salt intrusion. I was a very, very young graduate from Delft, just a master's student, and I was sent to Mozambique to help the government after the Portuguese left it without any senior staff. And I was made responsible for the hydrological division of the ministry, and I got a lot of requests. One of them was here in the Limpopo, and look, it's hand-drawn by me. There were no computers at the time, and I was not such a nice draftsman, but you can see here the Limpopo estuary where farmers suffered from salinization, and they asked me to look into it and help solve the problem. So what I did was go into the field and actually observe. So set up staff gauges, set up places where people took samples, and also I took a boat. I got a boat and I went along the estuary. On the horizontal axis you see the distance from the sea, and vertically you see the salinity. And all these, yeah, I would say clumsy curves that I made, drawn by hand, illustrate now when I look at this how deprived I was of theory. I just went there and measured. But I also found an important conclusion, because when you look here, you see that the salinity, when you are well out of the saline influence, is still high. And I could conclude that the salinity that these farmers here were suffering from came from upstream and not from the sea. But you could only find that out by going into the field and observe. But this led to a lot of theoretical development. Later, when I became less clumsy with my measurements, I could actually measure at the lowest point of intrusion, which is called low water slack, and at the highest point of intrusion, and then fit my theory. And here I only had the low water slack in 1980, but later I was able to do 2 surveys, both at high water slack and at low water slack. This can only be done with a speedboat. It's very fascinating to do. And you can see that it nicely fits the lines, who are theoretical lines, that obey this extremely simple mathematical equation, which is driven completely by the geometry of the estuary. So here the theory followed the observations. And yeah, of course, I published these things. So if you look at the date, 1986, and the staple you see is real, because at that time, your papers were actually sent to you in hard copy with a staple, a package that you could hand out to the world and send to libraries. And so there was a whole sequence of papers that followed from these early surveys. But then came my academic period. So rather late in life, I joined the university, and I had the benefit of having access to students who could, like this one day, my students generally enjoy themselves enormously when they go into the field, but now they could check the theory by observation. And they did that very nicely. This is one of my students from Malaysia, Jacqueline, she's sitting here, and they measured 6 completely unsurveyed estuaries in Malaysia. If von Humboldt had been alive, he would have liked this. And she was able to test the theory completely independently with new observations. With these results, these are 6 different, completely different estuaries with different geometrical qualities. And as you can see, the theory fitted nicely. And she could even develop that in a predictive method that was recently published. Now let me move to the tidal hydraulics. This is also an early picture. This is not myself, it's somebody else there. I'm not that handsome. I mean the one in the middle. And we also did a lot of tidal observations. And that these tidal observations, when you go into the field, you notice how remarkably simple the flow in an estuary is. The equations are highly nonlinear. they can assume very strange values. Nonlinear differential equations can do very funny things. But I observed very natural patterns. And I thought, if that is what I can observe, then there must be analytical solutions to these equations. So I started to look for these analytical solutions. And this was my first paper, where I got one solution, here a next, and this continued for some time. But when I got access to students and scientists, I could let people do this big time. And one of my students, Irving Zhang, applied this theory to the Yangtze channels. And we published this nicely in Hess. And you can see here that the geometry of the Yangtze branches fit these very beautiful regular exponential curves, and that also, when you look at the tidal propagation, the measurements follow the theory very, very nicely. And these are all relatively simple analytical solutions. They are summarized like this. These equations, we are not going through them one by one, and I'm also not going to ask you afterwards if you still remember them. But what you should remember is that the ones in the middle are different from the ones that you see in the classical literature. So these analytical equations are a little bit more complex, but they are really fitting the theory. And this book, which appeared with Elsevier in 2005, summarizes the theory. It's now out of print, but following that, I have prepared on a website the whole theory, which is completely accessible and which deals with shape, dynamics, mixing, and salt intrusion all in one. Am I going back? What am I doing wrong? Okay. This is the website. Those of you who are interested in estuaries, please go to this website. Everything is open access. You can download applications, spreadsheets, all the articles are there, and the PDF of the paper. And here you see an overview of all the applications of this theory in different places in the world. Of course, my first observations in Africa, but then also many in Asia, and some in Europe, and South America and the States. And you can even see, well, this is von Humboldt's region, so I've also done some in his field. Now I go to the flood surveys. Here you see a happy young hydrologist during an extremely dramatic event. This was during a tropical cyclone in Mozambique, where many people suffered. So as a hydrologist, you are not allowed to be happy with this. But as a scientist, this happens once in a lifetime. So I had the opportunity to measure an extreme event, real life. And that is something that is unique. You see here that this is the road, the normal road, and you see the sign here, of which the top is about 2 meters, and the road is on a dike. So you can imagine how deep the flooding is. So we were actually using the road to know where we were going. And this was a man sitting on his house in the floodplain. You can see that the house is probably some 2 meters high. And I asked him to come in my boat and I could put him to safer ground. But he said, no, 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 I'm safe here. If it comes up, then I go. And my goats are also safe. I don't know if this will float, but he thought that it would float. But he was right. This was the top of the flood, so he was safe. And these were the kind of instruments that we used to go into the field. It's not exactly the quality of von Humboldt's material, but it served the purpose very well. Now, this is the Inkomati that in 1984 suffered from terrible floods. And you can see here how the river comes from South Africa here, then travels north, and then south, and then comes here, and it meets quite a couple of stations where we surveyed the flood, and you see how it changes shape, and when it spills the bank, it becomes very flat, and then you have these nice slope curves. It all looks very old-fashioned, but this report actually helped Mozambique a few years ago when they had again a big flood. Because institutional memory is very short, and sometimes stuff that people did long ago still help to understand what's happening now. And these were the kind of instruments we were using at the time. And it's all, yeah, you would say maybe rather primitive, but it worked very, very well. And we were able to get a rating curve which also deals with the floodplain flow, because we measured all the flow over the floodplain. It was really complex work. And this is one of the rating curves in my life that I trust, because I did it myself. But when I sent a student of mine out to Malaysia to calibrate a new model, she said, this model can't be fitted to the data. I said, yeah, but if you have discharges, please also ask the authority for the water levels. They were very reluctant to give it, but she's a charming girl, so she got the water levels in the end. And this is what you get when you plot the water levels to the discharge. The colors are different years, so you see that the office makes a new rating curve for every year. And of course, the observations they have are the ones here, and then they just extend the double logarithmic line, and that's how we hydrologists get our data. And there are people who say rating curves are unreliable and we should deal with uncertainty, but I'm an engineer. I say, well, look, this is just hydraulic engineering. We know the processes of our rating curve. We don't need to deal with this uncertainty. We can deal with the problem. We can correct the rating curve. So I asked my student to calibrate on the water levels that were actually measured and to use the coefficients of the rating curve in the calibration process. And this is my student, by the way, and also she did real observations in the field, let's say in the tradition of von Humboldt. And I'm clicking, I'm doing my best. This was the place where she did that. But this is a very old method, which is actually in my lecture note. It's called Stevens' method. I don't think many of you know it. But it's a very simple method. And it makes use of the fact that the rating curve is in fact a sort of a Manning equation, whereby the topography, the geometry of the section determines this part, and this is the slope and the roughness. But the geometry, we know. We can determine the geometry when we just go to the field and we measure the geometry. And we can extend it even beyond the levels where we have water level observations. The only thing that we don't know is how these two factors are. And in fact, the discharge should be linear with this topography. So you can get the exponent of this rating curve from a field observation. You don't need to calibrate that. The only one that you have to calibrate is the linear coefficient. You put that in your hydrological model and you calibrate on the water level. That's easy. And you don't have to deal with these terrible uncertainties that people say there are. Now what she found is that the real rating curve was the black one. And she also did some field observations herself, and it fitted the black one. And when you use the black one, all of a sudden the historical data could be very well modeled by the hydrological model. The last subject is the one on rainfall runoff modeling. Again, here we are looking at a river in Mozambique, because that's where I actually started doing rainfall runoff modeling. But maybe the most fascinating one was dealing with the ungauged basin, the Luangwa, which lies between two major reservoirs. This is Kariba on the Zambezi, this is Cabora Bassa on the Zambezi, and this is a major tributary to the Zambezi, but which is virtually ungauged. That means we almost know nothing about it. And that's extremely important, because this Mozambican reservoir is operated to mitigate floods, but we don't really know how much comes out of this major catchment. So we started to go into the field. The green line is what we traveled with the car. We made some observations, we looked at the landscape, and that was about all. We, by the way, installed a gauge here in that point so that a year later we could at least check our model against that gauge. But we went into the country and we just looked at the landscape. We made these kind of sketches. We think the system works like that. We translated it into some model structure, and then we started to model the catchment, and we tried to calibrate it on gravity information from space. And in fact, we could predict the floods from this ungauged basin. It was a lumped model, but we accounted for distributed drivers. So here you see the precipitation in a distributed way, here you see the soil moisture, and here you see the evaporation. So it is a lumped model structure, but distributed forcing and a distributed accounting. But everybody knows that landscape matters. The hydrology doesn't work the same on a steep hill slope in the mountains or in a low-lying area. I don't have to explain you are not hydrologists, but if I tell you that hydrologists model the world as if there is only one landscape, then you start to doubt if hydrologists are doing the right thing. And in fact, this is what they're doing. But landscape matters. And if you want to transport a catchment from one place to another, you have to take into account that landscapes are different. And landscapes we can observe when we walk in the field, but we can also observe from space. And in fact, digital elevation models already tell us a lot. This was what drove me to write this discussion paper on topography-driven conceptual modeling. And the idea behind it is that if you have a landscape which consists of lowland, not in the sense of elevation, but lowland meaning close to open water. That means that the land is not much above the open water, not more than a few meters, which means the hydraulic head of the landscape is low. And this is steep land, and this is more or less flat land, but high above the nearest drain. This is a typical European landscape, and that leads to different hydrological mechanisms and different hydrological conceptual models. And that worked very nicely. My student Sheva Harari took a relatively small catchment in Luxembourg. This is the topography, the elevation. So the red part is the highest, a bit above 500 meters. And then we looked at the height above the nearest drainage. And there you see that these same parts that are red here are blue here. That means on top of the catchment, apparently the open water is very near to the ground. This is what I call a wetland. In a wetland, the water is relatively close to the surface. So you can have that on a water divide. And also the slope in this same area is low, which means that we classified that area. Here you see a light blue, that this area on the divide and also this area on the divide is classified as wetland. Now when we classify the landscape into these three classes, wetland, hill slope and plateau, we see that we can get the hydrological processes much better and that we also can separate which mechanism is at work. Now this is a European catchment, and von Humboldt would agree with me that Europe is rather simple as compared to tropical areas of the world, and also the tropical areas are far more interesting. So I give you an example of this landscape-based approach for China, which is work by Hongkai Gao, a PhD student of mine, who has also a presentation this week. And a paper that we published in Hess is testing the realism of this topography-driven model. And this catchment in China is a semi-arid, or you could even say an arid catchment, which has mountains, it has wetlands, it has hill slopes, and it has not much data. It has data at the outfall, and it has 2 subcatchments where we have data. But there's not much rainfall information. It's really an outskirt. But it has fascinating combination of landscapes. It has mountains, it has wetlands, it has hill slopes that are green, it has hill slopes that are forested. It's a beautiful combination of different landscapes. And Honkai was capable, by using purely topographical information, to reproducing these land use classes that have been developed independently by ecologists. And then we had a landscape classification which corresponds with certain hydrological processes. And these different subcatchments, the GG is the total one, and these 2 are the subcatchments, they have different landscape combinations. So if we would apply the model or calibrate the model to the entire catchment and then check inside, you have different landscape combinations, and that's a good test if landscape actually contributes something to our modeling. It did. And this is just a simple representation of how this topography-driven modeling works. The nice thing is that these landscape elements are connected through the groundwater and by the drainage network. And here we go back to these 3 subcatchments, and then we can see that if you calibrate on the entire catchment, you validate on the entire catchment, and if you validate on the 2 subcatchments, you get very good results. I'm not going into details because that's something that only hydrologists will find interesting. But let's go back to von Humboldt. Is this Casiquiare Canal something real? How can water flow from the Orinoco to the Rio Negro and from the Rio Negro to the Orinoco? As a hydrologist, this can only be the case if that area is a wetland area. So if this is a water divide where the water is relatively close to the surface, and if it rains a couple of kilometers on this side with a thunderstorm, it will drain this side, and if it rains here, it will drain the other side. But it can only be if it is a wetland. Now let's check if that is the case. This is the head. So that is the height above the nearest drain. So in the red part, indeed, we see the light green color, but we see the light green color in many more places. In fact, this Rio Negro is an extremely wet part of the Amazon. It's really flat, because if I look at the slope, you see it also almost has no slope. So the area that we are talking about has almost no slope and almost no hydraulic head. And when we combine them into these wetland classes, you see that a very large part of these catchments, and particularly also where they connect, are wetlands. And this is also what von Humboldt wrote in his diary. He said it was infested by mosquitoes. If they hit their hand was full of blood, you know. So it was infested by mosquitoes. It's really a huge wetland area. And here you see it zoomed in. By the way, what's interesting is that these areas that look a little bit higher, we call them terraces, they are partly because they are on natural levees, but partly these are also trees, because these digital elevation models have difficulty seeing the difference between trees and land surface. But you can really see that this area here is extremely flat and wet. So, the Orinoco and the Amazon are connected by a huge wetland. I'm somebody who doesn't speak too long, although my daughter disagrees with me. But I will close off with some concluding remarks, and then the floor is open for questions. But first, the concluding remarks. in my experience, theory followed observations. And the main reason was, it was not because my tutors didn't say. So my tutors said, read the theory, then develop a concept, and then go observe. That was also what they told me. But as a young man in Mozambique, where did I get access to the theory? It was the time that the only fast way of communication was the telex. And with the telex, you were allowed to write 10 words, because every letter cost I don't know how much. So the telex you didn't use, and it was definitely not fit for stories. You could use the telephone, but that was also extremely complex and extremely expensive. So what you used was writing letters. And it took a bit more than a week for a letter to go from Africa to the Netherlands, and another week to come back. So sometimes I asked people in the Netherlands, and also my former professors, can you help me with this problem? Do you have literature that I can use, or whatever? But by the time they replied, I had already started thinking. So I had already started my own theories well before I got access to the classical theory. And this may seem like an inhibition, but for me it has been an enormous resource, that I was forced to dream up theories myself. And I can tell you, if I had one good idea, there were first 10 failed ideas before that, of course. It's never that you see the light immediately. You walk into many dead ends before you hit the jackpot. But if you follow the classical theory, you are absolutely certain to miss the jackpot. Because you walk in the well-trodden path, and it is a dead end. Because otherwise, other smart people would definitely have done it before you. Because I'm not stupid, but I'm definitely not as smart as all these other people who have done all this work before. So if you are not so smart, you have to think for yourself. I hope this is a nice point for discussion. And after you have developed your theory, it leads to completely new concepts. You can sometimes find new things just because you observe, you theorize, or something like that, and then you come with new concepts. Now, I'm 100% confused also. I'm 100% convinced that we can only do good science and new science by observation. And that can be lab experiments, but I think the richest new ideas you get from field experiments and from field observations at whatever scale, small scale to large scale. Field observations are crucial. And I guess there are also many people who teach at universities. Please send your students out into the field. Drag them away from the computer, get them into the field, let them dirty their hands, their feet, and everything. It will be an inspiration for them. And this is what we need. Not only to ground check your ideas, but to be inspired. And I think that's fully in line with what von Humboldt did. Von Humboldt would never have been able to develop his standard works without going into the field and observing. Now, that was the story I had to tell. I think I have not put you to sleep. So thank you very much, and I look forward to some discussion. Maybe Günther?
Thank you very much, Hubert, for this fascinating talk. We have a quarter of an hour time for questions and discussions, actually. So any comments you would like to make, any questions, please? Yes?
There are microphones there if you want to.
Yeah, please come forward to the microphone because it's a big room. In the main corridor.
I shall summarize the question. Is that okay? So,
My problem is how do we measure the flood level? So that is
yeah.
non-spatial.
So what you're saying is it's not only the gauge changing, there can be really big morphological changes in rivers that make that rating curves change over time. Yeah? That's in fact what you're saying. And yeah, I think my only answer to that is you have to continue to do observations. But you see that most discharge measurements are done at relatively low flow because the very high flows are exceptions. So the low flows will tell you how much the riverbed has gone down or how it has changed. So if you do regular observations of low flows, that's perfect. But I think you should accompany them by topographical surveys that tell you in which direction the rating curve will develop at higher water levels. And what you can of course also do, you make a hydraulic model of a stretch of a couple of kilometers and you see what your hydraulic model does. So that would be another way of recalibrating your rating curves.
Okay, thank you. More questions or comments?
Yeah, please come to the microphone. Yeah.
Thank you for your nice story. I was actually wondering, now that you say first measurements, then theories, does this basically mean that you have to be free of prejudice?
Yes,
which is
that's what
basically
it
impossible?
means. Yeah, that's it. I must be honest, I was not free of prejudice. In fact, I tried to remember the things that I was taught. Yeah, I tried to remember, but I wasn't completely, I knew more or less in which direction to search, but I didn't know exactly. So I was not free of prejudice, but in general I would say yes. But it doesn't apply to myself, I'm afraid.
Okay, thank you. Yes, in the back.
When you talked about the flow of water in estuaries, you described the equations as very complex and non-linear, and yet the phenomena you saw were quite simple. When you derived your particular theory of this, how did you decide which dynamics to retain and which ones to leave out?
Yeah, thank you, Ross. Yeah, I don't know. I tried a lot of things. I really tried a lot of things. But if you know that the solution of a complex differential equation is a rather simple equation, you start to look at where can I find this simplicity. But it is not something you can do easily. Well, there is one approach that is taking away all the higher order small changes. So you scale and you start to neglect the higher order or smaller errors. This is not what I did. That's a sort of a perturbation theory. I didn't do that. I did it in a different way and I found a different solution. But how you do it, I don't know. I mean, how do you get inspiration? It's just by trial. In fact, I sat in front of the tent. I was camping with my wife and I was thinking about this and she said, "What are you thinking about?" And I said, like all men do, I said, "No, nothing." She said, "No, yeah, you're thinking about something." I said, "Okay, then I'm going to buy a notebook in the shop and then I'm going to write down what I'm thinking." And that's how these derivations came. I don't know, Ross, if it helps you.
Okay, thank you. Yes, please.
Vasken.
Hubert, you mentioned that Alexander von Humboldt lied, and that he lied that it was for the good of science. But which limits would you impose to the scientist in lying? When is lying good for? Can it be good for science? When can it be bad? Are there limits in your opinion?
Yeah, I think a lot of people have written books about the ethics of science, and I think nobody said that lying is allowed, but lying to a politician, I think, is allowed.
Okay. Nobody's questioning that. Yes, in the very back, please.
Jesus.
In Spain, we say that he who robs a thief is forgiven. So lying to a politician is also forgiven. And Humboldt stayed in a long time in Galicia. So he knew how to do it in a graceful manner, so no problem. No, the question I wanted to ask you, or the point I wanted to raise again, is this theory follows observation. Yeah, it's a nice statement. It is true that there must be a lot of interaction. But the way you reply to this lady saying, no, I had even forgotten what I had learned in school, that is way too much.
Yeah.
If we start from scratch, everyone, forget about science. Science as a shared enterprise by everyone. We do things when we know what others have done.
Yeah.
So, of course, if you go to the extreme, then you're in trouble. But come on.
Yeah,
qualify things, and you can do it a lot better.
I watched the audience. There were a couple of my students in the room with these yellow shirts. They had to leave because they have to do what he does. He's also a student of mine, by the way. And I only said this after they left. So you can be rest assured, Jesus.
Okay. More questions? Yes, in the front, please. Please use the microphone.
What happened to von Humboldt when he got back to Spain and had to report to the Prime Minister?
Now I have to remember what the book says, but I think either the guy had died or he was no longer the Prime Minister. I think the problem was solved anyway.
Okay. Any more questions? If not, yes, there is one, please.
So, Hubert, I liked your story about how you got stuck in Africa and couldn't communicate the way we do right now, which gave you time to think about things really through. That seems like the ideal excuse for professors not to process their email. However, I think that you would also not be happy if your students replied once in 3 weeks to your emails. So how do you think that young scientists could achieve the same, I don't know, thinking space to come up with their own ideas?
Yes, Rolf. This is difficult because we live in such a dynamic world. It definitely has advantages. And Marco and I wrote a paper together through the email without ever meeting. So this modern technology gives us enormous potential, but it also has a drawback. But definitely the solution is not leaving the email for a couple of weeks before you reply your students. I don't know. I leave it to you and the young generation to find out how you can retain creativity in this dynamic world where you are continuously flooded by new impulses and new information.
Yes, creativity, indeed a keyword. Okay, maybe we make the creativity the final note. Thank you very much, Hubert, again for this fantastic talk.
Thank you, Günther.
Before you're leaving, an announcement. In half an hour from now at 1:30, in this room there will be a talk about water in terrestrial systems by Kurt Roth. This is one of the talks for a general geoscience audience. So even if you're not in the area of water, it is targeted to be appealing to a broad group of people, all of the EGU members. Thank you.